Well, thank you so much, everyone, for being here. I am so excited to um, start my role as the 2026 president of the Macro Energy Systems Society. I've been a huge fan of macro energy systems since 2020, since it was founded with Sally Benson, and I'm just really grateful to be here. So if you have ideas for the society, for different directions, for ways we can connect better, I'm always open to all ideas you have connecting everyone together. So just a couple of reminders. We're having the 2026 Macro Energy Systems Workshop at Georgia Tech. Hopefully you all got your abstracts in. Those were due March 1st. And then we also have a jobs board that if you're hiring, post there. If you're um, looking for jobs, that could be a great place to look. And then we have an email list, a newsletter. We have this recurring meeting, which happens monthly, and it's the monthly MES meetings. And this is the early career seminar. So we'll get started. Okay, so I am the president this year, and then I'm really happy to be accompanied by by our vice president Anthony and our treasurer Amro. Anthony has done so much work behind the scenes, and we're so grateful for him. And then the rest of the board, I'm really excited to join here. That we have on our right, Micah and some other folks have led the workshop committee, and they've done a tremendous amount of work. And I'm really excited for that this summer. So this summer in August, we'll see each other in person at Georgia Tech, and there will be lightning sessions, keynotes, interactive working sessions, a reception, lots of networking and community building. And again, shout out to the workshop committee for their massive amount of work that they're doing, putting that together. And I just have a screen clip of the first macro energy systems folks who founded this society in 2020, and I was reminiscing, rewatching some of those videos, and just really proud of this society and how far we've come. So, I also want to shout out the Macro Energy Systems Fellows. Um, Malik, Carla, Megan, and Dimitri are doing wonderful work in lots of different areas intersecting with energy systems, including energy justice, air pollution, climate impacts, and industrial heat. So that's exciting. Um, and the fellows are leading these initiatives. They've been organizing the monthly macro energy systems meetings that rotates between a hands-on tutorial, early career research seminar, and expert panels. And we'd love it if you have ideas for these hands-on tutorials, or if you want to give an early career seminar, or if you're interested in these expert panels too, please help definitely reach out and contribute your ideas. Additionally, ways to spread your new research and your job postings and other announcements are with our Macro Energy Systems newsletter. So awesome. With that business, I will get going with my short talk here, and then we'll have um, two other speakers, Nils and Wilson, follow after me. So that'll be great. Awesome. So weather constraints guide energy storage opportunities. I'm really excited to talk to you all about that today. I'm an assistant professor of civil and environmental engineering at University of Iowa. I just started this January um, after um, my postdoc at Stanford, and then I did a PhD at Caltech on long duration energy storage, which is what I'll focus uh, on talking about today. I just like to say that I grew up in Iowa and I found my way back to Iowa after 10 years in California, and I'm really happy to be here at Iowa. So I lead the LEAP lab on low carbon energy analysis and planning, where we analyze natural resource constraints, guide technology innovation, and target decarbonization solutions. We've got a couple grad students joining, and if you're interested in the future, let me know. So, yeah. So, load following electricity is a difficult to decarbonize sector, and it represents about 12% of global emissions, and it's kind of the focus of my talk today. Here I am showing wind, solar, and demand data for average across the continental US And right away, you can see these two multi-day wind lulls, which are a challenge. Um, but these wind and solar constraints give rise to opportunities for energy storage technologies such as multi-day energy storage to fill in for these multi-day wind lulls. Additionally, you can have curtailed other or wasted electricity beyond demand. And interestingly, this gives rise to opportunities for low efficiency energy storage to potentially soak up that need if it's cheap enough. Um, so various wind and solar constraints include extreme weather years, droughts and seasonal lulls, and curtailed or wasted electricity. But these give rise to energy storage opportunities, such as multi-year and seasonal storage functional roles, large volumes of low-cost energy storage, and uh, opportunities for low efficiency energy storage if it's low enough cost. I've published in all of these areas, but today I'll focus primarily on the energy storage story. I want to say that various technology options may provide load following electricity. We'll hear from Wilson next about geothermal, which is a source of clean, firm power. Sector coupling can also help with load following electricity. But today we'll talk about long duration energy storage as one option from a menu of options. Um, and I'm showing examples of long duration energy storage here, which include like an iron air battery, like form energies. There's compressed air energy storage, pumped hydro, and underground hydrogen storage as well. Um, yep. So we asked, at current technology cost, would long duration energy storage reduce the cost of reliable wind solar battery systems? Um, One example of long duration energy storage, as I mentioned, is underground hydrogen storage, where you can take excess wind and solar electricity. You can use it to split water into hydrogen and oxygen, store the hydrogen underground, and recombine it with oxygen in a fuel cell to meet electricity on demand. Um, and these two energy storage technologies, they both have charge steps, storage steps, and discharge steps, but importantly, they have opposite complementary cost structures where where the long duration energy storage technologies typically have very low energy storage costs in this middle column, but higher charging and discharging costs. Um, so just for comparison, um, lithium ion batteries, they're projected to get lower in 2050, but not orders of magnitude lower. This cost of $2 a kilowatt hour is far lower than the predicted 2050 costs of lithium ion batteries. Um, and these costs are really what drive our results. Um, we weren't, our priors going into this study, though, were not necessarily that this underground hydrogen storage technology would be cost effective, but uh, basically because in our priors we saw the high charging and discharging costs, and we also saw the very low round trip efficiency, and so we did not expect it to be present in the least cost system. However, we found it was. And it was primarily because of that very low energy storage capacity cost. So here you can see the excess wind and solar beyond demand uh, charging up storage, and then discharging during a summertime lull in wind and solar. Um, so this is a seasonal lull that the energy storage is filling in for there. Um, Additionally, uh, we considered multi-decadal weather data sets because we wanted to understand the value of seasonal energy storage. And in order to understand the value of seasonal energy storage, you have to look at multiple seasons of weather data. Um, and that was typically not done by utilities and regulators. And so that was new. We looked at 1 year, 3 year, and 6 year horizons, and we found that reliable systems that plan for more years increasingly depend on long duration energy storage. So here you can see the max storage capacity was about 10 days of mean US demand when solving the model for a single year um, compared to closer to a month. Um, Additionally, you can see multi-year energy storage being valuable, where uh, energy storage is built up here over 3 years and then depleted during a scarce, stressful event later on. So yeah, the key research advance here was twofold, that we used multi-decadal weather data and we modeled an emerging technology. And I, this paper is mainly cited for just the simple fact that long duration energy storage can reduce the cost of reliable wind solar battery systems. Um, and we bound that system by saying wind solar battery systems. Um, so yeah, it was cited in policy by Canadian and Australian governments, and that was really cool to see the work move from academia uh, to practice. Additionally, we looked at other energy storage options. We looked at redox flow batteries, pumped hydro, gravity storage, thermal compressed air energy storage, metal air batteries. And we found that geologic hydrogen storage and metal air batteries, they were the most cost-effective energy storage technologies, again, because of those really low energy capacity costs. Um, so don't think of me as someone who's like a hydrogen person. Think of me as someone who's focused on low energy storage capacity costs. Yeah. Um, but we did consider uh, in more detail underground hydrogen storage because it is a promising example of long duration energy storage, and we looked at underground storage constraints specifically from natural gas infrastructure, and we found that if you were to repurpose about half of the available um, natural gas storage facilities for pure hydrogen, um, that would be enough for national scale seasonal energy storage in some of our models. So there's ample capacity in existing natural gas infrastructure. Additionally, you might be saying, well, all of your results are only looking at wind solar storage systems, and emissions are not allowed. But here we looked at systems where natural gas was allowed, but then it was increasingly constrained at different time periods or over time. And we found that underground hydrogen storage can reduce electricity costs in wind and solar systems when natural gas is restricted to like about 15% of demand. So this means that long duration energy storage is really a deep decarbonization technology, and it's not competitive today while natural gas or while other dispatchable sources of electricity are not constrained. So it's a deep decarbonization solution. Next, we looked at the value of different innovations in underground hydrogen storage, including the value of capital cost improvements compared to the value of efficiency improvements. And we found that if you took our base case and looked at a 7% system cost decrease, or uh, uh, sorry, a theoretical improvement of efficiency, round trip efficiency from today to 100%, the system cost would only decrease by about 7%. Whereas if capital costs were to be minimized all the way to zero, then system costs would decrease by 35%. So um, we found in this system that capital cost improvements were more valuable than efficiency improvements. And that's because we were looking at a wind solar battery system with a lot of curtailment. And these systems were not, the storage systems were not highly sensitive to inefficient utilization of abundant zero cost electricity. So um, that was the specific system we were looking at. Um, Additionally, we've looked at dirt cheap energy storage, thermal energy storage in dirt, which uses soil or rock to store energy at very, very low capital costs of 1 cent a kilowatt hour. So I mentioned $2 a kilowatt hour for underground hydrogen storage, about 5 to 10 to 20 for iron air batteries, and then lithium ion was on the order of 200 or $300 a kilowatt hour. This is so cheap in comparison. And uh, additionally, we considered thermal energy storage at decommissioned coal plants where you can repower the steam turbo generators. And this repurposing means that you can also take advantage of a very low discharger cost of about $250 a kilowatt. Um, and that makes this energy storage technology incredibly cost effective. We found that it was um, competitive even without an emissions constraint in a wind, solar, gas storage, and oil system across the continental US. Um, so this you can see that the thermal energy storage in dirt, it's not replacing all of the natural gas, but it's filling this seasonal energy storage role and meeting these challenging times where there are both wind lulls and demand peaks in those summer times. Yeah. So the primary tool that I have been using to discuss the previous papers that I mentioned is this macro energy model, which is a weather-focused single node capacity expansion model that is really useful for considering multiple decades of weather data. But now we're looking at multinodal sector-coupled modeling with spatial resolution in Pipes of USA that's been developed at Stanford by Kamran and Trevor Barnes. Um, and some of the first paper that I'm using Pipes USA to look at is asking this question of, is hydrogen still valuable for long duration energy storage in sector coupled energy systems? And what we found is that huge underground hydrogen storage was still valuable, but instead of hydrogen getting re-electrified in the power sector, hydrogen was more valuable as a chemical feedstock. So here you can see the we still have a large hydrogen storage capacity in these sector coupled systems, but the capacity of either fuel cells or hydrogen turbines were much lower in the sector coupled system. And this work is in collaboration with folks at University of Michigan. So yeah, today I've talked to you about how wind and solar constraints guide energy storage opportunities, specifically for long duration energy storage. I talked about the wind and solar droughts and the seasonal lulls that are these resource constraints. And we talked about guiding technology innovation and different energy storage technologies and which types of innovation are most valuable for reducing overall energy system costs. And additionally, we discussed repurposing infrastructure for
It's what,
decarbonization, including
9:30 I'm already playing video games.
oh,
That'd be too much.
I think somebody unmuted. Oh, sorry. Okay, yeah. And finally, we looked at repurposing infrastructure for decarbonization solutions, including using these natural gas underground storage sites for hydrogen, and also repurposing decommissioned coal steam turbo generators for thermal energy storage. So with that, I will say thank you so much, and we should move on to Wilson. So thank you all so much.
Awesome. Thanks, Jackie. I am going to see if my share screen works from my browser, so bear with me. We might be having trouble here. Let me see if I can find my.
Oh, if you're having trouble, Nils could go next potentially too. So whichever you.
Let me give this a shot.
Okay, Wilson.
Try sharing my entire screen.
Okay, nice. You got it.
Can everyone see this presentation
Yes.
in presentation mode?
Yes. It looks
Excellent. Okay. Well, thanks everyone for being here. Thanks to the MES board for inviting me to talk today. I'm also a member of the MES board. I was MES president 2 years ago before we were officially a society. And right now I am at the electricity program at Clean Air Task Force, which is a international NGO focused on essentially decarbonization by any means necessary, but primarily focused on advanced technology development and the role that technology innovation can play in accelerating decarbonization. Um, what I want to talk about today is actually some research I put out middle of last year. There's a paper published in Joule based on work that I did in my previous role as a PhD candidate and postdoctoral researcher at Princeton University. So this presentation today is going to focus on enhanced geothermal power, which I'm sure a lot of the audience is already reasonably familiar with. But just to recap, EGS, as it's kind of colloquially known, is one of a fairly small number of kind of promising candidates to fill the role of clean, firm power generation. So that's resources that can deliver carbon-free electricity whenever needed and for as long as needed. And geothermal power, conventional geothermal power, is an existing clean, firm resource, but very limited in terms of its geographic availability and just total potential because it relies on these very unique geologic features, naturally occurring superheated underground reservoirs that we can tap into. Enhanced geothermal systems are a method of creating artificial geothermal reservoirs and essentially unlocking the ability to generate geothermal power anywhere you can find hot, dry rock, which is basically everywhere if you drill deep enough. And so the estimated potential of enhanced geothermal systems in the US is many tens of terawatts, potentially even hundreds of terawatts of electricity generation technical potential. And there's been interest in EGS power for a good 50 years now, going back to the 1970s, the Fenton Hill project. But recent advancements in things like directional drilling technology and hydraulic fracturing, which actually came out of the shale oil and gas boom, have really spurred a new wave of enhanced geothermal development interest. And it seems like this technology is much closer to prime time than it ever has been. If we kind of look at the current state of EGS development, there have been a few major technical milestones in the last few years alone. Especially since I started working on this back in 2020, there's been really incredible progress. The first really large-scale modern EGS demonstration came with a pilot project by Fervo Energy, which is kind of the leading private EGS developer right now, in Nevada in 2023. That was only a 3 megawatt project. There was also a successful flow test at the Department of Energy's demonstration project in Utah, which is more of a science facility than a really commercial scale generating facility. And more recently, Fervo, right next to the DOE's Forge site in Utah, published results from a 10 megawatt flow test of a well there, and they claim to be bringing online up to 100 megawatts of enhanced geothermal power at that site by the end of this year, with a target of 500 megawatts by 2029, and PPAs signed for that. So this is a technology that, again, 5 years ago was kind of largely theoretical and now seems much farther along the road to prime time and demonstration and commercial availability. And there have been pretty significant advancements in things like the cost of drilling at these sites, which was a big unknown. It's kind of been shown that you can actually drill fairly quickly and cost effectively, even in hard granite basement rock, which was a kind of major source of skepticism of the ability to do EGS right, that the drilling technologies could only really work well in softer shales, like in the oil and gas sector. But there's been a lot of progress, still a lot of remaining uncertainties. So I don't want to say that we're in the clear and EGS is just here. There's long run behaviors that need to be investigated, things like how well the reservoirs perform over time, how well they retain their heat, how much water losses into the subsurface can be constrained, and various other things. But we're very much in kind of the ramp up phase for enhanced geothermal power right now, with a lot being done on the ground. And so when I kind of was in the process of planning this work, I think there were a few things that we had in mind. One was, of course, this reality of kind of major advancements on the ground, and the first real pieces of field data that we had on this technology, so we could kind of stop being, maybe be a little bit less speculative about what its cost and performance would be. At the same time, of course, the expectation of growing pains that this is a technology that is really just taking its first baby steps on the commercial stage, and that past studies, which I and others had done, kind of examining the role of EGS, its potential in future electricity systems, really looked out to, say, 2050 and assumed availability of this technology at competitive cost and commercial scale. And of course, in reality, as a nascent technology, it's going to face scale-up constraints. It's probably going to see its costs start higher and come down over time via economies of scale, workforce scale-up, learning by doing. We see this phenomenon with all sorts of emerging technologies in energy and elsewhere. And so there were a few key open questions that I wanted to look at, like where and when might early commercial EGS become cost effective, become kind of commercially competitive? And then how would the kind of scale and timing of those initial deployments affect its learning trajectory and its long run deployment potential? And ultimately, what is a realistic long run potential for enhanced geothermal power over the next, say, 3 decades? And so this study kind of broke into 2 parts. The first was a near-term cost baseline for enhanced geothermal power, actually incorporating some of this latest field data to try to estimate for the first time what an early commercial project might cost. And then using this kind of cost data as an input to a national scale multi-stage capacity expansion model, using the GenX open source electricity system model that was developed at Princeton and MIT. And what's interesting about this particular study is that we were using endogenous learning rates. So for enhanced geothermal power, as well as a few other emerging clean firm technologies, we only set costs in the initial stage, and then their costs in future stages are based on the amount that's actually built in prior stages. So if there is never any commercial investment in any of these technologies, their costs never come down. And again, and this is kind of focused on commercial phase deployment. So we're assuming that above market investments are made to actually demonstrate these technologies. I think it's unlikely that we would see a first of a kind project get built by a model if that was all we gave it as an option. I'll also note that this study was done prior to the Big Beautiful Bill, and so we had a couple of scenarios, one which was current policy, which was the Inflation Reduction Act at the time, and the other was kind of a more aggressive net zero policy. We also looked at a total repeal of the Inflation Reduction Act, and it turns out that the reality is kind of somewhere in the middle, where we kept the subsidies for clean firm, including geothermal, at least through 2035 for the time being. And so I think, just to caveat, this is a challenge of doing anything resembling a projection in energy system modeling. Policy can kind of change under our feet, but I think it's also a lesson in how to kind of try to keep your results as useful as possible, model as many scenarios as possible. It turns out that reality probably looks something like our kind of current policy scenario, at least from the perspective of geothermal power. given that subsidies for that technology have been retained. In terms of the approach, this is, of course, using a national scale electricity system model, 15 zones with fairly high temporal resolution, scaling down the geographic resolution to accommodate the flexible geothermal optimization submodule that we developed in prior work, which represents the ability of enhanced geothermal systems to actually modulate their power production and kind of make more efficient use of the heat resource, which is a limited resource, and also make efficient use of the power used to pump water through the system, which can be kind of shifted in time by storing pressure in the reservoir. And this is something we'd investigated in pretty high detail in prior work, and incorporated into this as kind of a key capability of enhanced geothermal power. We developed national scale supply curves for enhanced geothermal. It's not a uniform resource by any stretch. It's highly geographically variable. And so to model it effectively, you do really need to be using temperature at depth maps and data sets that reflect that in some regions it's much more easily accessible at lower depths and lower costs. And we also simulated the operations of an enhanced geothermal system using an assumed reservoir design. This is on the left, and based the kind of cost the cost baseline on an assumed initial reservoir design. So very much ground up. And then this is just an illustration of the flexible operation model. We calibrated this using actual multi-physics reservoir simulations of these systems undergoing flexible operation. But this is just showing that the optimization model that I built based on those simulations pretty much replicates the simulations exactly, while being extremely much less complicated because it's fully linear. And this lets us basically fully capture the kind of weird but pretty important behaviors of these systems when they operate flexibly. Moving on to results, I want to start with just the cost baseline we built. This, again, is based on as much of the published data from these demonstration projects as we could access publicly. And it's, of course, there's a pretty high range of bounds, but the general conclusion is that within uncertainty bounds, outside of the Western interconnection of the US, where the best quality resources are, EGS is almost certainly not going to be initially cost competitive. And that makes sense. It's, you have to drill very deep east of the Mississippi to access high enough temperatures. Within the Western interconnection, it's another question. And specifically at what we call near field sites, these are areas close to existing known conventional geothermal systems where you have hot water kind of welling up and bringing heat higher, to shallower depths than you'd find it normally. In the areas around those systems, you can find near field enhanced geothermal potential that is really quite promising from an early commercial perspective, and is likely where we'd see initial deployment. And it's much, much cheaper than kind of the deep baseline. And again, here's an example of just commercially developable sites at different depths. In the left plot, this is all, you have to be above 150 Celsius to kind of be developable at all. The left plot, we only see those labeled sites, which are the near field sites, having some capacity, and it's still fairly large capacity potential. And then at 6.5 kilometers on the right, you see much wider potential. This is on that map alone, that's probably multiple terawatts. And again, you still have those same near field sites, but it's, you can go almost anywhere in most regions. In this particular temperature depth mapping, and I'll get to, there are some uncertainties. Oops, sorry. So yeah, that's the kind of baseline supply curves. Um, I want to then get into our modeling results of pathways to scale, which is, and this is showing essentially when we throw EGS into the model at different near-term cost assumptions and under different scenarios for policy, does it actually get off the ground? And by how much? And the answer is yes. And under supportive policy, we see enhanced geothermal having very, very high potential, particularly because of this dynamic of having early potential at sites where the costs are much lower than the national average. So these near field sites, even if your costs are for the technology as a whole are initially high, the fact that you have sites where it's much more, the resource is much higher quality means that you could still potentially have commercially competitive developments even in those early stages. And that provides kind of the jumping off point to, if your costs come down over time via learning, those cost reductions allow you to move up the supply curve into the kind of lower quality resources while remaining cost competitive. And this provides kind of a runway to get to commercial scale, which is something that wind and solar have both benefited from. The fact that there are certain sites that have much higher resource quality than others, like the Midwest for wind or the Southwest for solar. The same is true for geothermal. And it's actually a kind of a disadvantage for some of geothermal's competitors, like nuclear or gas with CCS, where the costs are kind of the same everywhere, and so you're either cost competitive most places or you're not, and so you don't have this kind of early market potential, or at least as clear of a pathway through that. Of course, in scenarios where either high costs or lack of supportive policy stunt early deployment, you see much lower long-term potential, which is kind of a illustration of how these things either compound on each other or the lack of activity kind of compounds on itself in a negative way. What's interesting is that in scenarios where we assume just baseline EGS costs and an assumed learning rate equal to our baseline assumption of roughly 15%, which is very similar to what was observed in the shale oil and gas industry, we see EGS eventually becoming a national scale resource, actually not even limited to the Western interconnection. And what's interesting here is that learning-based cost reductions, despite the fact that there's still a very large difference in resource potential from west to east, the magnitude of that difference becomes lower as the magnitude of the overall cost becomes lower. So instead of 100, or $200 a megawatt hour versus 100, it's now 50 versus 100, and it's only a 50 difference. And so we actually end up seeing quite a bit of development in the eastern half of the country being plausible. And just back to what I noted earlier, we do have, there are significant uncertainties in the actual resource, the temperature at depth mappings. On the right here are results downscaled to the actual sites of individual project deployment for two temperature depth mappings. The top one was from Southern Methodist University. It was the only existing mapping for a long time. And then the bottom one is a more recent mapping out of Stanford by Mohammed Algebran and Roland Horn. And what's interesting is these maps disagree a lot on where, where the heat resource is and what its magnitude is. But Model 2050 total deployment across these scenarios where we have identical things except the resource-based assumption are almost identical. So the total geothermal deployment is almost identical, but location of that deployment varies a ton. And the conclusion here is that sufficiently high quality resources probably exist to support national scale deployment, despite the uncertainties in where they are. But practically, we really need to know where the best sites are to actually realize this potential. And so, there's a lot of disagreement in the data we have right now. And so better mapping and exploration are going to be absolutely critical to unlocking very large scale geothermal deployment. Lastly, I just want to talk about plausibility because, of course, we can, model out assumptions till the cows come home. But what's relevant is, are there actually plausible pathways to the cost reductions that would enable national scale deployment? And the first thing I want to note is that people often talk about cheaper drilling costs, which have come down in the early EGS development phase. But we're close enough to the oil and gas kind of standard now that, barring major technological developments like energy drilling, we can't really expect further cost reductions to come from just cheaper drilling. Um, on the other hand, just like in the shale industry, we could expect most of the cost reductions that we observe in the model learning to come through improvements in the actual design of the artificial reservoir. So increasing the number of lateral wells, adding more vertical layers of laterals, increasing their length. These are all approaches to maximizing the amount of flow you can get while minimizing the amount of drilling you have to do. So your drilling isn't necessarily cheaper, but you're getting more water out per well and accessing more rock per well. And if you add up all these potential, I think fairly plausible kind of developments, you get to a very high level of cost reduction that is sort of similar to what we observe in our cases where we see very deep learning. And so there are plausible pathways here, though, of course, real world validation is very much needed. And I'll just conclude by saying that, again, these results are showing that EGS could very plausibly, at current estimated performance, grow to become a very large source of carbon-free generation if we can manage to achieve large-scale deployment in the next decade. If it can meet that target and benefit from those cost reductions, the resource is sufficient to actually act as a clean, firm power resource across most of the continental US, which is something that I think has not really been, was not my prior expectation going into this study. I mostly assumed it would be a Western only kind of thing. But learning curves are learning curves. And even if it's more expensive in other places, it could still be quite valuable. So TBD, look out for that. I'm going to stop sharing my screen now. And I will pass it on to the next speaker. Thank you all.
Awesome. Thank you, Wilson. All right, Nils. Thank you.
Yes.
That was great.
Give me a sec to share my screen. Do you see it do you see the presentation? Yeah. Cool. Yeah, thank you for having me here. Thank you for being here. Thanks to the MES board. Today I debated presenting between two studies, one using Pipes of USA and looking at transmission expansion and long duration storage. But I instead decided to talk about floating offshore wind, which is also an emerging technology at a slightly different stage than EGS that we just heard from Wilson. And that's not very favored today in the US, but a lot of the people in the industry are ready to go, and abroad is being developed quite fast. So I wanted to talk a bit about that today. This is a study that we're looking at global potentials, and I'm currently a postdoc at Stanford working for Inesh Azevedo, and there's another couple people working on this whole project, which are Edgar Verghese and Professor Steve Davis. Just to give you a little bit of an idea of what the talk is going to look like, I'm going to talk about some background on the studies. Then I'm going to focus on the first part of the project, which is the technical potential, and then I'm going to talk a little bit about future work. This whole project is at very much earlier stages than the previous two that we heard from Jackie and Wilson. So it's preliminary results. It hasn't been published or anything, but still wanted to present that. Give you a little bit of background. My first paper during my PhD was a review paper published in Annual Review of Environment and Resources in 2023. And we looked at the global technical economic, and feasible potential of renewable electricity. And what that means is that we looked at every paper that looked on the global scale at one of these three potentials, technical, economic, or feasible, for at least one renewable technology. And we did that originally while, Dinesh and I worked with the IPCC, and we realized that there was a lot of disagreements between studies on what the actual potential of each renewable technology was, and also some of the definitions were a little different from a paper to another. So we wanted to clarify those definitions, qualitatively determine what were the most important factors, explaining the differences of results, and then come up with our own qualitative range of potential for each resource. And just to make sure that you all understand what we mean by technical potential, which is what I'll talk mostly about today, it's that it's the amount of electricity that can be produced in available and suitable areas, given current or soon to be developed technologies, specifications, and efficiencies. And so if I'm explaining that simply for, let's say, onshore wind, you would look at the whole amount of wind that there is on the planet. Then you would determine areas where you could actually install onshore wind. So you'd remove oceans, very like terrains with very high slopes, things like this. And then you determine, okay, what if in all of these areas we deployed wind turbines at a specific spacing and everything, and then you take into account the conversion efficiency of wind turbines, the wind resource in those locations, all of that, and then you determine, okay, technically with what the technologies we have or we understand, we could extract this much energy. And, oops, sorry. And the main conclusions from the paper were that technical potentials are widely used in literature. The method is relatively common from a paper to another and similar to what I'm going to describe today. Economic potentials that I'm also briefly going to touch on are not as developed and not as used in the literature, but they do have some values and have some important indications on where the resource could be tapped in at economic prices. And then the third definition we looked at is feasible potential. And our conclusion was that you can't really do this on a global scale because it takes into account a lot of political, social, environmental, and cultural constraints, which are just extremely hard to apply on a global scale and require much more spatial granularity. So yeah, so let me talk a bit about the technical potential of floating offshore wind and how we're trying to calculate that. Of course, you need to assume some parameters on what the wind farms are going to look like. So we're making assumptions on the turbine size and hub height. Then we also need to assume how spaced out those turbines are within each farms. And we're assuming a 5 megawatt per square kilometers. These three values that you're seeing here for the turbine hub height and farm density are from an expert elicitation with floating offshore wind experts that we performed 2 years ago, and they predicted what the industry was going to look like in 10 and 20 years, according to their opinions. Then we are also including losses. Not all of the energy available is, of course, turned into electricity, so we're accounting for array losses, availability, electrical, things like this. And the very important step for the technical potential is what I was talking about earlier, determining the suitable area. And for that, you use exclusion layers. I'm going to come back to it in a second. Once you have determined those suitable areas, you then look at the wind resource in those areas. And for that, we're using wind data from ERA 5, which is on a 0.25 degree spatial resolution, which is not super high and would be a problem for onshore resource, specifically because there's a lot of difference of terrain and a lot of the onshore wind resource can actually be located in very small pockets versus offshore there's no obstacles and the resource is much more constant, so that kind of resolution is actually okay. We're using hourly data. We're only looking at the 2024 weather year for now. I might run it for other years as well. And the data is at 100-meter altitude that we turn into 150 wind speed to match the hub height and using power law, which is common in those studies. And you then have to turn this electricity, this wind resource into electricity output using the power curve from a wind turbine. All of this is pretty standard. What I meant by exclusion layers and how to determine the suitable area is you have to apply all of these constraints. So for offshore wind, obviously you first start with bodies of water, oceans, mostly in some places lakes, like in the Midwest, you could look at the Great Lakes. But then we're looking only at economic exclusive zones. We don't consider that you could deploy floating offshore wind in international waters, be too complicated legally. Then you have to apply some depth and distance from shore constraints. Since we're looking at floating offshore wind, we don't look at any areas below 60 meters depth because that's where you would have fixed bottom offshore wind, the other more mature technology that taps the offshore wind resource. And then we're applying a depth limit of 1,300 meters, which is broadly accepted in the industry as feasible. A lot of people say you could actually go deeper, but this is what we're using for now. You also don't want the turbines too close from shore, nor too far. It wouldn't make any sense. And then you exclude a lot of areas. We excluded any area that freezes sometimes. There are some technologies that could handle that, but for now, we're just excluding them. We're excluding marine protected areas, heritage areas, bird and biodiversity areas. And we also take into account some other human infrastructures and activities such as shipping lanes, fishing areas, submarine cables, oil and gas infrastructures. All of that is included in our analysis and excluded from where you could deploy offshore wind. We also consider that you wouldn't really have, in the technical potential, technically, you have those suitable areas. You just look at how much energy could be produced in those areas. We're also applying a threshold on you actually need decent resource, and we're removing areas with capacity factors below 20%, which would be very low for offshore wind. So yeah, we're just removing these as well. This is an example of how a map would look like with all the exclusion layers. This is for Italy, and some exclusion layers are not visible just because they don't exist in this area. But the way the code works, the way my code works is that it goes per country. So you see all of the boundaries are the economic exclusivity zone. Then in red, there's the protected areas. In blue, in the north, you see some high fishing zones. All of these are excluded. The purple are the shipping lanes, and it's where there's been a lot of shipping activity in each of these pixels on average over the last 5 years. And all of these have different spatial resolution. And what we're doing is that we're just overlaying these exclusion layers with the suitable areas, which are in green and have the 0.25 degree resolution that I mentioned earlier. And we're just subtracting all of these areas from the green pretty much. So it was just to give you an idea of what it looks like. And then once you have this and you have all of the green areas where you know you could have offshore wind, you use the wind speeds from Era 5 that I was talking about earlier, turn it into energy production based on the actual area of the grid cell, which gives you the total capacity of offshore wind that could be in each of these grid cells. So you end up with a total energy production per grid cell. What you're seeing here is the potential based on the capacity factor class, where this is just to have a visualization of how much of the resource is being subtracted because of this capacity factor threshold that I talked about earlier. In almost all of the countries that I've ran so far, it's very little. As I mentioned, 20% is a very little capacity factor for offshore wind, which are usually much higher, around 30 to 55%. So we can see here in Italy, a lot of it is between 30 and above 40. And for example, in Brazil on the right, it's very high. The final map results for the technical potentials would look something like this. Again, this is preliminary results and not my final my final maps, but it would look something like this. You have Japan on the left, Brazil on the right, and Brazil in the middle and Italy on the right. It shows you where the resource is very high. In southern Brazil, for example, my here it goes from 0 to 25 terawatt hours per year, which makes it look like the resource is actually not that great in any of these grid cells. This is too high. It should be around 20, which would make it look a little better. And it's the case in my new figures, but just a little side note. And one thing that I'm uh, showing as well in these maps is I look at the 2023 electricity demand from the EIA I'm using, or yeah, anyway, I forget which exact source I'm looking at, but one of the major international ones. And I'm comparing this potential to the electricity demand in each of these countries. And in a lot of these countries, you see that it's huge. Like in Brazil, it's 10 times the electricity demand. In Italy, even if it doesn't look that great, it's still equal to the total demand. So these countries all have huge technical potentials. Japan doesn't have it because this is an earlier version of my code. Yeah, so this is what it looks like, and I just wanted to briefly talk about some of the novelties of this, since as I said, these are common methods. First, we updated technological parameters which hadn't been done in a long time on a global scale. The turbines used to be assumed to be much smaller, but the industry has grown super fast and is expected to keep growing. So this has been updated, which of course means the hub height is also updated, and usually means faster winds, better resource. The depth limit also used to be much lower in previous papers, and we're increasing that. Only a few were using 1,000 meters. And we also include more exclusion layers. A lot of the human activities were not really included on global analyses, partially because some of the data was not available at the time. And we actually found that some of these are really important, and we're going to run sensitivities on them. And the few next steps that I haven't finished for the technical potential are including military zones and nuclear waste disposal sites. But a lot of this data is not really available globally. And as I said, running a lot of sensitivities. I'll come back to it in a second. I just want to briefly talk about the future work, which is more innovative and novel. And it's just going to take me a minute. I'll be quick. The economic potential, as I mentioned, is still something that has been used. You just take the total capacity in each of these grid cells, calculate the cost, and divide by the production in that grid cell. And it gives you an LCOE for each of these grid cells. I also want to look at the levelized cost of transmission, trying to determine how could you connect these grid cells to the existing grid and potentially demand centers like cities. And I also want to look at the correlation of the offshore wind resource with the onshore existing renewables. And for that, I would be using some data from electricity maps, which I don't know if some of you are familiar with it, but it seems to be relatively new and they have a lot of cool stuff. So if any of you know about it and would like to discuss, I'd be super happy to, because I discovered this only a couple months ago. And also look at hourly market prices and potential revenues for offshore wind. And the ultimate product of all of this is to have an online tool dashboard. It's been done for other technologies. The Global Wind Atlas also looks something like this, where you could have the technical or economic potential show up for the whole world. You could look at it per country, and then you could toggle a lot of the different parameters based on our sensitivities that we're going to run with different sizes of turbines, hub height, exclusion layers, and all of that. So that's the final goal of the project. Thanks.
Yay! Thank you, Nils. That was awesome. And thank you everybody for joining. I really appreciate it. Those were those were great talks. And if you have questions, feel free to reach out to any of the speakers. We really appreciate you guys being here. And also, if you want to give one of these talks, definitely let us know. We're always looking for people who are excited about giving early career research seminars. Thank you so much, Niels. That was awesome.
Thanks,
Yeah,
Jackie.
that was great. Thank you, Malik. All right. Well, if nobody has any questions or anything else to say, then we can say bye.